Welcome everyone. We'll kickstart this 32 minutes past. One thing I'll ask, if everyone could please put yourself on mute, that would be much appreciated. So welcome everyone. For those who haven't been to this community of practice, sustainability on concrete, I just want to welcome you all. For those who don't know me, because I'm still very new to the industry, my name is Olivia Alexis, and I work for Cement Australia as the technical product specialist. So, for those who haven't attended the community of practice before, the main aim of this, group is just to really understand where the industry is currently at, where we're moving towards, and bring both the industry as well as researchers together to exchange ideas, advancements, best practices around sustainable concrete. So, the main aim is to really understand how are we, putting things in place in which we can decarbonize our industry, both in concrete and also civil materials such as cement, steel, and other things like that. So our previous community of practice was held in March, and we spoke about sustainable infrastructure. We had two speakers, one from Transport New South Wales and another one from University of Queensland. Oh, sorry, UTS. Apologies. So the main aim is just to really understand, what industry is doing and what the academic world is doing, and how we can collaborate more efficiently as a means of achieving our embodied carbon goals and decarbonizing the industry. So today's community of practice is specifically on Alum Sludge. Fortunately, we have two speakers, Alex Keegan from SA Water, and also Yuan Lui from University of South Australia. So today's topic, and it's been quite a popular topic, which is really interesting, and I'm really interested to hear our presenters and understand their findings. But the main aim of today's topic is to understand the potential operation and repurposing of alum sludge, both in the water industry and perhaps in the broader concrete and cement industry. So before I hand over to our first presenter, which is Alex Keegan, I would just like to mention some housekeeping rules. So for those who haven't attended the COP, basically both speakers will present, and then at the end we'll have sufficient time just to ask any questions. And I prefer for this meeting to be very interactive, so feel free to raise your hand at the end of both presenters, or you can easily add a question in the chat. Also, just to reiterate, please turn yourself on mute, and also this is a recorded session. So without further ado, I will present our first speaker, Alex Keegan. Dr. Alex Keegan is the Manager of Environmental and Biological Sciences at SA Water. With a 24-year research career in water and wastewater sector, she has a wealth of expertise and has been involved in the managing of the life cycle of a range of nationally and internationally funded projects. Significant work includes developing methods to validate pathogen removal and activation in wastewater treatment processes and COVID surveillance in wastewater, leading to significant outcomes for South Australia Water and other Australian utilities. Her background includes 12 years with SA Water's world-leading laboratory arm, Australian Water Quality Centre, and the past 4 years managing the environmental and biological science team. Please welcome Dr. Alex Keegan. Over to you.
Thanks, Olivia. Can I just check, can you see my slides, and is my voice coming through okay? We didn't check that before.
Yep, that's
all good. Cool. Sorry, it's just a different system. So thank you, everyone. So I'm just, now let's see. Oh, that's right. Sorry, I think there's a bit of a delay. So I'm just going to talk about some of the challenges that we've faced in SA Water around alum sludge. And sorry, I just need to move your faces over to the side because I couldn't see. So I'm just showing the schematic of what happens in SA Water. We deliver water and wastewater services across the state of South Australia. Up the top here, we've got all our different types of bulk water that comes in, and all of these go through one of our 41 treatment drinking water treatment plants. and gets delivered to customers. And then all of this comes back out from residential customers and also from businesses in the form of wastewater into sewer. Dropping down the bottom here. Can you see my pointer there, Olivia?
Yes, I can.
Yep, cool. All right, thank you. And then goes through one of our 29 wastewater treatment plants. The indicative thing in this part of the presentation is that we have 9,338 kilometres of sewage mains, and that's important in terms of how we're looking to utilise the alum sludge that we've got from our drinking water treatment processes. If we move on, sorry, this is a bit slow. One of the challenges we've had over the last few years is what to do with our alum sludge. So we call it water treatment residual. So this is the product that comes out of our drinking water treatment process. It can contain a whole range of organics and also some contaminants as well. At the moment, we're producing around 17,500 tonnes per annum. And what you're seeing on the right-hand side here is a range of different stockpiles that we've got of alum sludge that's coming out of our drinking water treatment plants. You'll notice that some of a little bit darker than others. We also have activated carbon that's added to these through the treatment process, and that's to remove taste and odour compounds. And so that can add an extra interesting aspect to the reuse of the alum sludge. We also have to classify our different water treatment residuals, and so this comes down to the different contaminants that are in there. So in some of our drinking water treatment processes for reservoir in particular, to control algal contaminants and algal growth, we actually use copper sulfate, and this gets removed through the drinking water treatment process, but ends up in the sludge. So what that does is increase the level of contamination that we have in that sludge. So these down the bottom here in the table is the indicative costs for disposal of our different qualities or different classifications of sludge. Intermediate waste is the cheapest, low level contamination, and then high level contamination. And you can see this is transport plus the EPA levy, $464 per tonne. And at the moment, this is costing us around $5 million per annum for disposal of these to landfill. So we wanted to come up with a better way of reusing this alum sludge and finding some value. What SA Water has done over the last few years is started going down the circular economy path and looking at some different options of what we could do. So beneficial reuse of what was deemed a waste product into actually making it a useful product. We do have a small amount of our alum sludge goes for tree planting. So this works as an adsorbent put into the bottom of the hole, and it's a water holding capability and helps the trees grow, and that's in our CBD area. Down the bottom here is the mine site rehabilitation that we've done. So this was a trial site looking at piling up the alum sludge, recovering any of the eluate that's coming off of that to make sure that that's not going and contaminating the land. Other options were around recovery of alum from sludge as one part of the recovery, or also metals as well, so copper. So we've found over the last couple of years that supply chain issues, especially since COVID, it becomes more difficult to access some of these chemicals, and so having an alternative way of recovering them is beneficial. And the last one is what we're talking about today, so that's around incorporation into concrete products. The other area, sorry, just moved that one, is around sewer erosion and corrosion. So we have what I've shown here on the right-hand side is for our Northern Adelaide area, the different types of pipes that we have. So you can see a lot of reinforced concrete and concrete pipes that are there. And what can occur in this instance is hydrogen sulfide attack, so acid attack on the concrete. In wastewater. So we wanted to look at something else of how to manage this. At the moment, it's looking like plastic pipes are potentially better, but throughout this process and these projects, it looks like there's the potential for fixing some of the pipe types by using alum sludge incorporating, and Yu's going to talk you through that. Oh, sorry, that didn't move on. I did get asked to just say a little bit about our engagement with Uni SA. So this isn't a brand new engagement piece. We've actually been working with Uni SA in different groups for as long as I've been with SA Water, so that's 24 years. So we started with a cooperative research centre for water quality and treatment when I came on, and the teams have been working together before that, of working on different projects, highlighting different areas that needed investigation. We provide support and supervision and training for PhD students, and then we also have the university side feeding in as well from expertise from the academics within the universities. We also have in-house laboratories, so we've got 2 levels of laboratories, micro level and also chemistry type analysis that occurs along with a commercial lab, so we can do a lot of this sort of thing in-house, but we also bring in expertise from the universities and Uni SA in particular for a lot of these things. From those PhD students that we have supported through, there's actually been employment of a high number of PhD postdocs into the business and into other parts of the business, not just into the research arm. And so we've been collaborating for a long time and sharing our knowledge and expertise and issues that come through. So through this project, what's been developed so far is, it's been 2 projects actually, 2 PhDs. So Yu's PhD was on alum sludge into pavers. So you can see that, I just need to move that one. Up here, so different percentages of alum sludge going into pavers and testing out how durable they are and making sure that they meet all of the requirements. And then also for our contaminated sludge, so this is for copper in particular, making sure that there's no leaching occurring out of those pavers as well. We've also got alum sludge into drywall for that really high level contamination. So there's no actual leaching that's going to happen. It's an internal wall, so there's no issues with wetting in there. And then the third one actually came from the university back to us, and that was around this cementitious material that you will talk about in a minute. So, oops, that didn't move forward. Oh, sorry, that's not moving forward. So potential uses that we have that have come out of this are for the production of green pavers. So this is only small scale. We only have a limited amount of alum sludge that comes out, but we're looking at what the best options are for this anyway. At the moment, it's not been decided that we'd go down any of these paths in terms of implementation. There's sort of future work that needs to be done. One thing could be cement pipe replacement. So could we develop a product that incorporates this alum sludge, and you will talk about the benefits that he's seen through incorporation of alum into the pipe, or potentially pipe relining. So what we need to do is really understand in a larger scale application of the corrosion rates and the durability. We have a materials engineer on site as well who would actually help support that through and with the university. We also have a wastewater chamber at Bolivar. So we're been trying to upgrade that to do accelerated corrosion rates in that as well. The Weiwei, one of the PhD students, has been using the chamber at ambient levels at the moment. So any of these options would require feasibility assessment, design considerations, all those sorts of things. But really the aims around it are to reduce costs for disposal, which is great. Also to reduce the waste that's sent to landfill, which is great. But the third best bit of it is beneficial reuse of a product into a better product. And that's me. So Weiwei, I think I'll stop sharing. And over to you. Sorry, it's you, not Weiwei. Sorry about that.
Perfect. Thank you so much, Dr. Alex. And before Dr. Yu comes through to share his presentation. I just give him a bit of an introduction. So Dr. Yu is currently an enterprise postdoctoral research fellow at the University of SA, a role selected by the Deputy Vice Chancellor and Research Deans from over 460 applicants, with only 10 being chosen. He completed his PhD in civil engineering from the University of South Australia in May 2022. Focusing on green construction materials in September 2023, Dr. Lui was awarded the Australian Research Council Discovery Early Career Research Award. Please welcome Dr. Lui. Over to you.
Oh, I just share my screen. You see my screen?
That's perfect.
Okay,
I
sure.
can see that. Thank you.
Hello, everyone. I'm Yue Liu. I'm here to present some more details about Alum Sludge as cement replacement. Actually, our group has conducted research on sludge for around 6 years. We found sludge could be used as sand replacement, cement replacement, and a geopolymer precursor. Today, I will only focus on cement replacement. As mentioned by Alex, in South Australia, the water industry use alum-based coagulant to purify the water, and so the received sludge is rich in aluminum and silica. But for raw sludge, there is a significant amount of for raw sludge, there is a significant amount of organic matters. These organic matters will heighten the cementitious hydration significantly. So we have to do some pre-treatment such as calcination and grinding is required to remove the organic matter and improve the reactivity of sludge. After pre-treatment, the aluminum and the silica content in sludge occupies around 80% of the total mass. These results indicates its pozzolanic reaction potential when used as the cement replacement. Because for cement, when it touches with water, it will generate some CIC gel to bind aggregate and fine aggregate and coarse aggregate together to make the concrete hard. For pozzolanic reaction, those aluminum and the silica content in sludge will react with the calcium hydroxide produced from the cement hydration to produce some secondary CIS gel. These some products we already developed, like concrete blocks, cement sludge mortar, and geopolymer mortars. For raw sludge, after crushing and grinding and calcination, we got this is exactly sludge powder we are using for cement replacement. And after pre-treatment, we can see the received sludge is slightly coarser than that of cement. And in SEM image, we can see the sludge actually shows irregular shapes. And the pozzolanic reactivity of sludge was measured by Ferranti test and the strength index test. Based on the results, we can find that sludge after calcination at 700 and 800 degree shows satisfying pozzolanic reactivity, but 800 degree is the optimum temperature to activate pozzolanic reactivity of sludge ash. Based on the chemical element mapping for the sludge and cement binder matrix, we found actually the sludge modifies the CIS gel by increasing aluminum to calcium ratio and decreasing calcium to silica ratio. Also, we found the formation of aluminum burning phases is promoted. In real practice, and we put the sludge into to produce some concrete blocks, and we found the sludge block actually shows long-term strength development due to the delayed pozzolanic reaction, and the 10% of cement replaced with sludge shows a higher compressive strength than the reference one at 90 days of occurring time. The delayed polyolanic reaction is because, as I said, normally the polyolanic reaction happens when the cement hydration produces enough calcium hydroxide. To further analyze the reaction mechanism of sludge in cement-based composites, we did advanced nano-indentation and also the selective dissolution method. This is the sample preparation procedures for the nano-indentation test. We put fractured pieces into the epoxy and then grinding and polishing the epoxy to achieve flatten enough surface for nano-indentation test. For the selective dissolution method, actually, we found that the reaction degree of sludge in samples with 10% sludge is the highest, which reaches around 39%. But further sludge addition leads to a reduction of the reaction degree due to lack of polyolanic, because we increase the sludge content, definitely reduce the cement content, also the produce the calcium hydroxide. This is the result for the nano-indentation test. For the nano-indentation test, actually, we combine the indentation, traditional indentation test with the EDS mapping together. That makes each mechanical response of each spot linked with its in-situ chemical analysis. Actually, we found that the original aluminum CS gel in pure cement paste is converted to aluminum-rich CS gel, and the aluminum incorporation has no significant effect on the hardness and modulus of CS gel. Also, we found the unreacted sludge shows much lower modulus and hardness value than the unreacted cement clinker. For sludge, probably the modulus value should be around 40 gigapar, but for unreacted cement clinker, it's around 100 gigapar. As we confirm the sludge can promote the formation of aluminum burning phases, then because some of the aluminum burning phases may have excellent high temperature resistance, then I did high temperature resistance of mortar containing sludge ash by assessing the mass loss, residue compressive strength, water absorption, and the UPV. Actually, I found the superior heating resistance mortar containing 10% and 20% sludge is confirmed. And for example, for the residue compressive strength, after heating to 800 degrees, a significant strength loss can be found in the reference sample. The strength reduced to around 28%, but for the samples with 10% and 20% sludge, it's retained its original strength to 43 and 47 respectively. After the chemical microstructure analysis, actually we found the improved high temperature resistance is mainly from two aspects. First one is the formation of some aluminum burning phases, like the formation of a molite and the CaHgl with high temperature resistance. Also, because the polyolanic reaction of sludge actually consumed some calcium hydroxide. For calcium hydroxide, it will be decomposed after heating to between 400 to 500 degrees, then produce calcium oxide. But those kind of calcium oxide will possibly rehydration during the cooling process. Then with a 44% volume expansion, those expansion will damage the concrete significantly. If we consume some more calcium hydroxide, then we can mitigate such a damage. This is the SEM observation for some samples after exposure to different temperatures. We can see the reference samples after exposure to 800 degrees shows dark color with porous microstructure, but for the sludge one, still the microcrack progress with the increasing temperature, but for the sludge one, actually the binder matrix still retained its properties. The color doesn't change too much. And final is there is a new type of cement, like we call the LC3 cement. It contains 50% OPC and 30% metakaolin and 15% limestone and another 5% gypsum. Because for metakaolin, it contains around 40% alumina. This is very similar to our sludge. So I'm thinking about if we can use sludge as an alternative for metakaolin to produce RC3 cement. That's why I conduct study like a scenery effect of alum sludge and limestone on mortar. And some interesting findings we found when we added both limestone or sludge, it shows a positive effect on packing density. That's because the inclusion of limestone and sludge with different particle sizes distributions widen the spread of bundle particle size, resulting in a greater packing density. And for the workability, because sludge got a very porous structure, absorb a lot of water, so it definitely will decrease the workability for concrete. But for limestone addition, actually slightly increased the workability. And for the strength, it's upwards combined limestone and sludge can contribute to the strength development. This can be explained by the chemical reaction of limestone in the ternary bundle system along with the pozzolanic reaction of sludge extended the contribution to the comprehensive strength development. For the porosity analysis, we can also see the combination of sludge and limestone shows a lower overall porosity than the reference sample, than the pure OPC samples. And compared with the OPC samples, sludge, combination of limestone and sludge actually refined the capillary pores. And yeah, probably that's all I want to discuss today. And if you got any further information, you can contact Professor Yan Zhuge. She's supposed to be here today, but she's traveling. So I present on behalf of her. Thank you. Yeah.
No, that's fabulous. You did a great job. Thank you for presenting on behalf of her. We really appreciate your time. Once again, I'd like to thank both Dr. Alex and Dr. Yuan. Really thank you for your time. Thank you for sharing your insights in regards to your findings around alum sludge and where you see, I guess, you overcoming the challenge that you currently have in specifically the water industry. So now is time for questions. I know most of our COPs, it takes some time for people to warm up and start asking the questions. So I have a few questions that I would like to ask the two speakers. But like I said, feel free to either raise your hand if you would like to ask either one of the presenters directly, or please just add some questions in the meeting chat. I can already see that one question came through, so I'll get on top of that. But feel free to send your questions through. So the first question I have is for yourself, Dr. Alex. Thank you again for sharing your presentation with us. My first question is, what's next in regards to your project around sludge in pavers? What are the next stages? I know you did mention that there is still a lot of research that needs to occur, but do you anticipate this perhaps becoming commercialized, or what would you say is the next stages?
So we are in discussions with a small company. They're an incubator type company who try and establish new businesses looking at making pavers. So that's one potential. It's been a bit of a slow burn of trying to actually move it into what the outcome's going to be. There are lots of different ideas across the business. One challenge we face is just around the volume of the residual that we've got. So within Yan's team, there has been a life cycle assessment looking at what SA water produces on its own. And in discussions, so Adelaide Brighton Cement are part of that project as well. For them, it's not a viable option to go down that path of producing any kiln, of transitioning a kiln over to dealing with the alum sludge. So we're thinking it's more like a boutique type brick maker or green brick maker, which might be a possibility. So there isn't a set plan at the moment, but looking at those different options. We are also looking at the alum recovery out of the sludge. So we have a few issues around suppliers and things, and that became apparent through COVID, that you couldn't always, and through a range of other things as well, where you can't always get the chemical that you need, and it's not about producing everything locally. We can't possibly do that, and we're also water and wastewater people. We're not all chemists. So looking at how we might do that, so alum recovery out of that. Also looking at, for us, one important thing is the potential, if we do continue to go to landfill, then trying to remove some of that copper, so that will decrease our costs. If we remove out the copper and take it from a high level contaminated waste to a lower level, then that can reduce our costs as well, or take it to intermediate, depending on how far we want to go. That, once again, is going to an external company to try and do those sorts of things. But for working with the uni, I see there being a need to sort of try and advance and look. So the work that's been done so far is on sort of small scale, little bricks and things. If this was made into a pipe, then how does that behave? What happens? How durable is it? How resistant is it? All those sorts of things, and comparing that against your standard, the standard pipe types that we've got, and seeing how that impacts for us. So that's sort of where we're going at the moment.
Thank you, Alex. And also, being in the cement industry myself, I definitely understand in regards to Adbri's stance on that. There's a lot of alternative supplementary cementitious materials in the market, and it's really important not to just look at its equivalent when you're looking at its comparison to replacing it into cement, but you also look at the availability and the quantity. We don't want to be having too many materials, I guess, that will kind of be seasonal, that isn't necessarily there for throughout the year at large quantities. So I definitely understand that stance. And I think it's still very good that you guys are looking at elsewhere in regards to how you can repurpose it, recycle it. Because at the end of the day, it is a waste. And I think we all are very much aware that we need to start repurposing our waste. So thank you so much for that, Alex. My second question was for yourself, but I'm going to tie that into Sam Chan's question because it was basically the same question. Curious to know if the sulfate content and the chloride content in the sludge after calcination, if it passes the requirements in AS 3582 Part 4, which is the manufactured pozzolan standard.
Yeah, actually, to be honest, we haven't done any test about this, but we do some. For example, if we make some sludge paver, we do some leaching test, like leaching test, like to see if some heavy metal can cause some leaching issue for our products. We already done that, but for that you mentioned, actually we didn't do it. But I believe the sulfate content in sludge actually is not that much. Yeah.
Just to add on to that, and just in regards to the manufactured spec, were you able to, I guess, sorry, I'm just trying to see, were you, sorry, I understand that you looked at the cash gel and understanding the extringite formation. With the inclusion of, I guess, the alum sludge, so increasing the amount of alumina in the material itself, does that impact early strength, or does that impact, sorry, not early strength, set time? Did you see an impact in set time by the increase in alumina?
Yeah, actually we did some study, or we already published our results. This is very interesting. Actually, I still try to understand why it happened, because when we increase the sludge content to 30%, we got a very quick sighting. That means this large amount actually accelerates the hardening process for the concrete or cement-based composite. But when we reduce this to 20%, it's delayed the the hardening process. So I'm still curious about why the 10 different can make such a different result. I'm still do some study on it, but based on our result, 30% can accelerate because we got enough aluminum. Aluminum normally is aluminum base is very earlier age formed, but why 20% is reduce such a lot? I'm still do some study on that part. Yeah.
Yep.
Thank you.
Sounds
Yeah.
good.
Yeah.
Perfect. Thank you. And a question for yourself, Alex, Dr. Alex from Dion. What discussions have SA Water had with regulators regarding reuse opportunities?
Sorry, which regulators do you mean?
Dion, did you want to quickly jump in?
Yeah, no worries. So the question mainly comes around, so the Vic EPA with their classifications on waste make it difficult to sometimes latch onto some of these opportunities, and we're wondering what discussions you've had regarding the use of this material.
So using it for the tree, or whereabouts do you mean you or using it into pavers and things?
Pretty much anything you've got to be helpful.
Oh,
yeah.
okay. So that's not come from my team or from this project. So we've got a circular economy specialist, David Daminato, who would be having those discussions. I can get back to you on that because I'm not sure. I know, well, I mean, the EPA guidance around that is that, I mean, there's concentrations for copper, and copper's the one that we usually miss in terms of making it into that high level waste. So actually being able to remove the copper, I don't see as being a problem. It just makes it a lower level classification of waste. For the pavers and things, so we were looking at leaching, or you was looking at leaching or leachability of copper and the like. That's why we looked at the two different options, one which could have the potential of having water coming onto it, as in like a standard paver, and the other being a dry wall, where that would be an internal dry wall, so that's not going to experience any water coming onto it. So no leaching happening in that space. So I don't see there being any issues, but we haven't directly approached them around using those types of products at the moment. Easy discussion to have, though.
Perfect. Thank you, Alex, and thank you, Dion. A question for yourself, Hugh, from Thomas. With respect to the concrete sewage pipes, the main cause of deterioration is acid attack rather than strength related. Has any work been done in this space in regards to the chemical properties and degradation?
Oh, actually, for sewage pipe, we just proposed a new project and got support last year. It's from Professor Yan Zhuge, and we supposed to reuse sludge as a supplementary sludge to produce some capsule. Because sludge contains high aluminum content, those high aluminum content we believe can mitigate acid corrosion. So we just proposed a new project, and starting from this year, and that's we develop a kind of a capsule. We put the sludge into the capsule, because if we put the sludge into the cement mix directly, it will got some post-landing reaction, probably reacted at the initial stage. So when the corrosion really happens, we may not have enough sludge to resist the corrosion. So we put the sludge into some capsule. Even if when the pH value, because the corrosion happened when the pH value drops. So when the pH value drops, the shell of the capsule will automatically dissolve into the solution, then release sludge with high aluminum content to control the acid corrosion. That's what we are doing now. Yeah.
Perfect. Thank you.
Yeah.
And a question from Rodrigo, and I should apologize from the start. If I pronounce your name incorrectly, I'll just like to apologize again. But either yourself, Alex, or you can answer this. Is raw alum sludge chemical composition stable and constant, or does it between plants differ? Is there any seasons in the year? Seasons in the year of any other parameters? I guess
I'll start. That's okay. I'll start and you can finish. So it does vary across the year in terms of what comes into the sludge, and that's because we have different throughout the different seasons. We have different things growing in the reservoirs. So we have cyanobacteria, blue-green algae, that grow in the reservoirs generally across the summer months, but that's extending out to being a little bit longer than that. We control the cyanobacterial growth by adding copper, And then so there can be copper within the sludge, because through the drinking water treatment process, the copper is removed into that sludge. What we also add in is powdered activated carbon. So what we can get with cyanobacterial growth and benthic cyanobacteria are taste and odour compounds. So that comes through as an earthy, musty taste and odour into the drinking water. So we add PAC and that actually removes it. So you'll see across the piles different sorts of colours depending on how much PAC's been added and that seasonality. So it does vary a bit. You might want to talk a little bit about how that affects your end.
Did you want to add to that?
Oh, sorry.
Sorry.
That's okay, thank you.
I'm reading through the questions. Oh, actually, for sludge, when we reuse as construction material, because the because the aluminum content will change with the season. Sometimes the aluminum content is a little bit higher, sometimes it's lower. But because, as I mentioned, the maximum reaction degree in sludge in the concrete can achieve around 39%. The most time, if we increase the sludge content to 20%, it probably just got around a 20% reaction degree. So the reaction degree actually is not that high. But this is common for the all supplementary cement material, like fly ash. Maximum can only achieve around about 30%. So if the reactivity is not that high, so probably the aluminum content change won't affect the result, like the concrete strength that much. We already did some tests, like we put different seasons of sludge and use the same treatment method. We got similar results actually. Yeah.
Okay, thank you. Thank you
Yeah.
both for your comments around that.
Yeah.
I'll just ask, I guess, 2 more questions. I believe I saw a question from Thomas in regards to putting some numbers, some embodied carbon numbers on this material. And I think this is quite important and quite interesting to talk about, mainly because when we start looking at, specifically if we're looking at cement in regards to reducing the embodied carbon in cement and then therefore in concrete, we really have to, if we're looking at alternative SEMs, increase that. And I know a lot of the work you did was around 10%. So have you looked at, I guess, putting a number on the embodied carbon, or I guess, as Thomas's question, for a carbon footprint around this alum sludge?
Actually, what we are doing is because we want to commercialize some of the alum sludge-based products, and we collaborate as a water producer CRC project, and to do some life cycle analysis, like or the supply chain design for the sludge products, and we close to get the exact number, like a social and environmental benefit we can get from different replacement percentage, but not yet. Yeah, we are doing something like that. Yeah.
Yep.
Perfect, thank you. And just a last question from Kanana. Using concrete made from alum as part of road building been looked at as a potential option? I think
it's okay because we already produced some pavers. As mentioned, it could be for road building, but I'm not quite sure it can be used because there are some road constructed by cementitious material. We haven't done any test about that condition, so I cannot answer. But for just precast pavers, we already did. Definitely can be used for road application. Yeah, because the strength of the paver we produced is enough for the pedestrian road and some side road, but not traffic heavy road because strength cannot be achieved that high. Yeah, to be honest. Yeah.
Perfect, thank you. And did you have any other additional comments, Alex, before we close the session?
No, not for that one.
No? Okay. Well, thank you all so much again for your time. If you do have any additional questions, because I know there were some longer questions, very specific questions, please feel free to contact either myself or even Yana from Smart Creek or Sawn or even our presenters. So once again, I would like to thank both Dr. Alex and Dr. Yu for your time. Thank you for sharing your insights. I wish you the best in regards to this project that you're working on. It's always really interesting just to understand different industries, because at the end of the day, we're all trying to decarbonize the overall concrete industry, and we all play our own part. So thank you all for your time, and please enjoy the rest of your day. Sawn, yeah, I see you want to jump in.
Just a quick one. Yeah, thank you very much, Olivier, and thank you, Dr. Alex Keegan and Dr. Yu Liu. It's a very, very good presentation and very good discussion. I see a lot of questions in here. So and now that as we are pushing for time, so there's so many relevant and very interesting questions. So is it okay we can provide a list of these questions, and maybe we can ask if you can view some of them, and maybe we can just get back to our participants today. We have over 50 people, which is very good to see a lot of people interested in this topic. So I'm pretty sure that there'll be more interest, and if we organize something similar in the future. So may I ask, we can list out all these questions that coming through, and maybe we can get back to you, the two speakers, and then see whether we can address some of them, and maybe we can do something with it. Okay.
Yeah, that's fine with me. I can't actually see the questions. I think we've got a firewall that stopped that, so I can't see it, but happy to answer anything I can.
Thank you. Thank you very much.
Thank you all. Have a good rest of the day. Thank you.
Thank you.